This is chapter 4, describing the relationship between two variables. So this is also called bivariate data. Bi means two, so bivariate data. So we're only going to cover the first two sections of chapter 4, section 4.1 and 4.2. I think that's only about half of the chapter. So if you're going through the textbook or practice tests or practice quizzes, just make sure you only go about halfway. We stop after the least squares regression line. So the first topic of discussion is scatter diagrams or scatter plots, which you might have heard of before, and then something called correlation, and then we'll get into what's called the least squares regression line. This is a relatively short chapter, and it's a very minor part of this course. So scatter diagrams or scatter plots are used to compare two variables. We're going to compare two variables at the same time. So a popular one is height versus weight. We're going to compare those two. Engine size versus miles per gallon. That's a popular one to compare. I always like to do homework grade versus test grade and see how those compare. So that's what a scatter plot is used for. One variable is considered the explanatory variable, while the other one is considered the response variable. So the explanatory variable is the input, just like back in chapter 1, while the other one is the response variable or the output. One is the x and one is the y, if you remember that from algebra. So the explanatory variable goes on the x-axis. I remember that because there's an x in explanatory, x-axis. The response variable goes on the y-axis, or the vertical axis. So we have the explanatory and the response, just like in algebra. So scatter plots can show several types of relationships. We are only going to focus on linear relationships, only on ones that make a line. There are other nonlinear relationships that exist if you take a more advanced statistics course or a research course or just any higher level math course. You'll study other nonlinear relationships. We're going to focus on the ones that either have positive linear, where most of the scatter plots are going up as the explanatory variable increases, the response variable increases in a nice straight line, or we'll focus on the ones that have a negative relationship. As the explanatory goes up, the response variable goes down, so it's a nice straight negative linear relationship. Both of those are linear. You can have other relationships. Projectile motion has a negative quadratic relationship, so it's a nonlinear. We don't really care that it's quadratic, that's just the parabola shape. There's another nonlinear. This is a cubic function. Remember that from college algebra. Not really important that we know that it's cubic, we just know that it's not a straight line. Then you could just have no relationship whatsoever, where the scatter plot points are just kind of all over the place and there's not a relationship. So this is where we're going to focus our attention, is linear. Just know that there are other nonlinear out there that you might study in your further down in your education. All right, so in the textbook there's a table of how fast you swing a golf club. So the golf club head speed, they measure how fast you're swinging, and they measure the distance that the golf ball travels. So these are different speeds that different people swung, and this is the different distances that the golf ball travels. This is one variable and a second variable. So I'd like you to plot them on this grid that I've provided for you. I try to scale it out. Sometimes the computer gets a little off in the numbering, but it should be scaled pretty well for you. I counted by twos, so you'll have to just go in between if necessary. Hopefully you can see that okay. And I'd like you to plot each x, this is going to be x, with each y. So I'll do the first one for you. If we have x is 100, I'll find 100 on the x-axis, and then I'll go up to 257 on the y-axis. So at 100, 257 will be halfway between those two, and I'll put a dot. So I'd like you to continue plotting the x and the y pair along the grid I provided for you. I'll give you a minute. And they don't have to be exact, just do your best. Plot each point as you see it. And you won't have to do this by hand. I just want to kind of show you how these all get plotted on the grid. As long as you can see it on the calculator or on an image, you'll be fine. 105, 277, 100, 263, 99. All right. So you might want to make those a little bigger so you can really see where each swing landed for distance. You have a couple that had the same speed but different distances. So same speed, different distances. And there's not that many points. I think there's 8, but it kind of shows you that the faster the club head speed is, the further your golf ball will go. The slower speeds had shorter distances, and the faster speeds had longer distances. So we have this linear relationship. If you take your pencil, you can kind of see that the dots roughly line up in a straight line. So that's called a scatter plot. You always want to label those axes so you know which one's which, and I always like to put a title of some sort on top. Here's what the textbook shows as their scatter plot. And it might ask a question like, what can you conclude from your scatter diagram? So you would say something to the effect of, the faster you swing the golf club, the further the golf ball travels. It looks like it has a nice kind of straight line, linear relationship. As one variable increases, so does the other. There's 2 types of linear relationships that we're going to study. Pretty straightforward. So if a scatter diagram shows a linear relationship, then it is either positive, which means as the explanatory variable increases, the response variable increases, or negative. As the explanatory variable increases, the response variable decreases. So what type of linear relationship does the golf data have? It has a positive linear relationship. Just a quick example of a negative relationship. I always think the gas in your tank, in your car, so how much gas you have in your tank, versus the miles you have traveled. So as the miles you travel increases, the further and further you go with that tank of gas, the gas level in that tank is going to go down. So as miles traveled increases, the gas in your tank decreases. That's just a quick example of a negative linear relationship. There's several others. I just think that one's a pretty common one that we notice every day when we drive. All right, so positive or negative, those are the only 2 options. So we check to see if it's linear. If it's linear, we look for positive or negative. Then the next question is, how strong or weak is this relationship? So we make this decision using what's called the correlation coefficient, which is a numerical value. Correlation coefficient gives us a number to help us make this decision. How strong or weak is this linear relationship? The book goes into this long explanation about how to calculate this by hand. If you look on your formula chart, there's a big, crazy formula for how to get this by hand, the correlation coefficient. You might just want to make a note to yourself that you can use the calculator for this. I don't want you to have to worry about this formula. It's got a lot going on, and it's just not necessary. Our calculator can give us this value. So we don't have to calculate this by hand. The calculator does this for us, and hopefully that makes you happy that we don't have to do all of that by hand. But it's called the correlation coefficient, and the discussion for it starts on page 180 if you want to read over it. All right, so the linear correlation coefficient is a numerical measure. It's going to give us a number between -1 and +1 that tells us the strength, and it also tells us the direction strength and direction of our linear relationship, and it's always between -1 and +1. We use a Greek letter, lowercase rho. It looks like a P. It's actually the Greek letter R, sort of. It's supposed to be an R. The computer always makes it look like a P, and it's kind of hard to draw it. It has a long tail and just a little tiny hook at the top. You really won't see that very much. We don't really deal with rho very much because it's the population's correlation coefficient, which we almost never have. We're going to be using the English lowercase letter r for our sample correlation coefficient. This is the one we're going to be using. We don't really see rho. We don't really use the population correlation coefficient. So it's kind of a funky symbol. Don't really worry about it. Just know that the lowercase letter r is the one we're going to use for correlation coefficient. All right, so we're going to use the calculator to find this value r. Before you start, you have to do what's called turning your diagnostics on. So in your calculator, if you push second, then the number 0, I know you probably can't see this, right above the number 0 is the word catalog. So if you push 0, it pulls up a catalog. And you're going to scroll way down, all the way down. You can kind of hold it and let it scroll. Let it scroll until it gets to diagnostic. It'll say diagnostic off or diagnostic on. You want that little arrow to be on diagnostic on. You hit enter twice and it should say done. And you have to turn those diagnostics on. Now they'll stay on as long as you don't reset your calculator. Some students will reset their calculator often. If you don't reset it, it will stay on. If you're not sure, just turn them on again. Second 0, scroll way down. You can always just turn them on even if they're already on. So make sure it says diagnostic on and the word done, so you have to hit enter twice. Alright, so we turn the diagnostics on. Now we're going to type in the golf data we use to make our scatter plot. We're going to put the club's head speed in L1 and the distance in L2. So go back to that page. Let me find it. I think it's the 4th slide, and it had the data for the club head speed. So we're going to put X in L1, and we're going to put Y in L2. So remember, if you go to Stat and then enter for Edit, I already did this. So you put in all your numbers for club head speed in that order. Be very careful to go straight down, don't skip any. And then you have to make sure the distances match up. So 100 and 257 should be in the same row, 102 and 264. So make sure they line up as you type them all in. I think there's 8. Whoops. So your cursor should be at the 9th position. There's 8. So I'll let you type all those in. Then we're going to push Stat Calc, which we've done before, Stat Calc. Instead of one of our stats, we're going to go way down to option 8, which says LinReg, which stands for linear regression. And it says A plus BX. That's the one we want, the one that says A plus BX. It's option number 8. You hit enter once. And then the newer calculators that will prompt you for L1 and L2, you should just be able to just keep hitting enter, and then it should spit out something that looks like this. If your diagnostics are not on, you'll only see A and B. If your diagnostics are on, you'll see an R squared and an R. And what we're looking for right now is this R value. Don't worry about R squared. We don't learn about that in this class. That's later on in chapter 4, and we don't cover that. So we're looking for the R value, and I like 4 decimal places, 0.9387. In your homework, they might want you to round off to maybe 0.94. So at least 2 decimal places. I prefer 4, just to be precise. So R is 0.94, just rounding off. What that roughly means is that the data are about 94% linear. It's kind of a percentage since it has to be between -1 and +1. The fact that it's a positive value tells us that we have a positive relationship. If it was a negative value, that would mean we had a negative relationship. So the sign of the correlation coefficient determines the direction of your scatter plot. So there's our R value. Keep that page handy. And with that number, we're going to interpret our correlation coefficient. So the closer R is to positive 1 or negative 1, the stronger the linear relationship. It's kind of like a grade out of 100%. So the closer R is to 0, the weaker the linear relationship. And I like to put this on a number line. I think it'll kind of help this make sense. This is just kind of the generic rule. If it's closer to 1, it's stronger. If it's closer to 0, it's weaker. But let's kind of make this a little bit more specific. And different textbooks have different numbers that make the decision. I believe these are the values that match up with this particular textbook. So any value between 0.8 and positive 1 is considered a strong, positive, linear relationship. Strong, positive, and linear. Anything between negative 8 and negative 1 is considered a strong, negative, linear relationship. So that's anything between negative 1 and negative 0.8, and positive 0.8 and positive 1. So the negative value just means that it's a negative linear relationship. Anything between 0.4 and 0.8. Some textbooks use 0.5. This particular textbook, I believe, uses 0.4. Anything in that range, from about 40%-ish to 80%-ish, is considered a moderate, positive, linear relationship. Anything between negative 0.4 and negative 0.8 is considered a moderate, negative, linear relationship. I keep emphasizing linear because this value will only judge linear relationships. And finally, anything between 0 and positive 0.4, anything in that range, is considered a weak, positive, linear relationship. And anything between 0 and negative 0.4 is considered a weak, negative, linear relationship. So again, emphasize linear every time. This value only judges how straight the scatter plot is. Not curved, not cubic, nothing, just straight. So how strong is the linear relationship for the golf data? We got an R value of 0.94. That means we have a strong, positive, linear relationship. So it matches up pretty well that the faster you swing the club, the further the ball will travel. It's got a strong, positive, linear relationship with an R value of 0.94. All right. So the book puts all of this information in a very big chart. Each one of these properties is something we've already discussed. We said R has to be between negative 1 and positive 1. We said if it's positive 1 exactly, we have a perfect positive relationship. If it's negative 1 exactly, we have a perfect negative relationship, which, to be honest, never happens. The closer R is to positive 1, the stronger the relationship is. The closer it is to negative, the stronger we have for a negative. So we discussed those. If R is close to 0, then little or no evidence exists of a linear relationship. Do note that just because R is close to 0 does not imply that there's no relationship at all. It just means that there's not a linear relationship. So just be careful there. The linear correlation coefficient is a unitless measure of association. So it doesn't matter what we're measuring or how we're measuring it. The R value is just a number. Then the correlation coefficient is not resistant. We discussed resistance in chapter 3. So an observation that falls way off the overall pattern, so if it's a big outlier, it will change the value of the linear correlation coefficient. So it's sensitive to outliers. All right, so that's kind of summing up all the things about a correlation coefficient. So the next slide, I have a lot of scatter plots with different levels of correlation. So we have a perfect positive linear relationship. Every single scatter plot dot is exactly lined up. That's when R is exactly positive 1. This has a strong positive linear relationship. Those points are fairly lined up. So R is pretty close to 1. This is a moderate. It's kind of all over the place. Notice the R value is much lower because the scatter plot's a little jumpy. Although if you still take your pencil, it's still roughly a positive linear relationship. Then we've got a perfect negative relationship when R is equal to -1, which in real life almost never happens. We have a strong negative linear relationship where R is close to -0.9. And then here we have that moderate negative relationship where they're roughly going down in a straight line, but they're just kind of all over the place, so your R value is much lower. Here's an example of no linear relationship when the points are just all over the place and the R value is close to 0. Here's another example. There's not a linear relationship. R is still close to 0, but you can see a very strong nonlinear pattern. So when R is close to 0, it could mean that there's nothing going on, or it could mean that there's something different going on that's not linear. So it just kind of sums up visually how the correlation coefficient looks. And that's on page 181 if you'd like some more details about that. All right, so this slide is a little weird. This is something I've only ever seen in this particular textbook, and I've seen a lot of statistics textbooks. This is the only one that has this weird little side note. This is to determine if a linear relationship exists. This book talks about comparing our correlation coefficient to what they call a critical value. And it's based on sample size. So it's based on your sample size n. So there's a table, it's table 2. It's underneath the random digit table in your booklet. So here's our formula page, then another formula page. Here's the random digit table we used back in chapter 1. Underneath that, you see table 2, and it says critical values for the correlation coefficient. And like I said, this is the first time I've ever seen it in this textbook. It's not in any other textbook I've ever used. So it has different sample sizes, 3, 4, 5, 6, 7, 8, 9, and then it keeps going 10, 11, 12, 13, 14, 15, 16, and it keeps going, and it keeps going. The one in the textbook has all the n values lined up, and it gives different values here that look like correlation coefficients. And they're all positive, so we don't worry about the sign. But what we do is compare the correlation coefficient we get, the absolute value, so we don't worry if it's negative. If our correlation coefficient is greater than the critical value from the chart, then we can say a linear relationship exists. So it tries to visualize it for you. The critical value will be determined by the sample size. Positive or negative doesn't matter. If our value is greater than it, either positive or negative, then we can say an association exists. If it's less than it, if R falls in the middle, then we cannot say a linear relationship exists. So it's a little weird. Remember R value, the R value for the Gulf data was 0.94, and our sample size, I believe, was 8. So the critical value, we'll look up in the chart. So we'll find the sample size of 8, and it says 0.707. And since the R value is greater than the critical value, we can say yes. And that's because 0.94 is greater than 0.707. So you just have to compare the correlation coefficient you get using the sample size to look up the critical value, and if the R value is bigger than the number in the chart, you're good to go. Otherwise, the answer would be no. I don't put this on the test. It's just, I think it's a homework question or two, but I do not put that on the test because that's just not something I've ever studied. It's only in this textbook. So it's in there. It's not hard to do. It's just kind of an extra check to see if the relationship is linear. All right, the last part of section 4.1 is just a quick discussion on the difference between the word association and the word causation. So lawyers are always very particular in their words, and they choose their words cautiously because you have to be very careful what you say. So we can never say that causation exists. All we can say is that there's a linear relationship or association. So to just be careful with our words. So in other words, we cannot say one variable increasing caused the other variable to increase or decrease. All we can say is that variable A is associated with variable B, whatever those variables are. We could even add the word linearly associated with variable B. So we can say that the speed of a club head, how fast you swing, has a positive linear association with the distance traveled. We cannot say that the faster club head speeds cause the ball to go further. That would be making too bold of a statement. We didn't run an experiment or anything, so we can't say that causation exists. There's other factors that determine the distance the ball travels. So we can use the word association, we cannot use the word causation. Just a quick difference between those two. All right, I will pause there and pick back up with section 4.2.